Class, today we're going to talk about volume of spheres. And before we see the formula and look at some applications of how to use the formula, I do think it's important to see where that formula comes from. And then once we have that formula, then we can start using it to solve some problems. So we're going to watch a short little video on where the formula for volume of a sphere actually comes from.
In this video, we're going to discover where the formula for the volume of a sphere comes from. In a previous video, we saw that it took two cones to fill a sphere with the same radius. So we'll now go back to recall the volume of a cylinder. And if we remember, the area of the base is pi r squared, since the area of a circle is pi r squared, and we can get the volume of that cylinder by multiplying by the height. We later learned that to get the volume of a cone, we would take the volume of the cylinder with the same height and same radius and simply divide it by 3. As we saw in the experiment, it took two cones to fill up a sphere with the same radius. It's important to note that that would mean the height of the two cones would be the same as the height of the sphere. And the radius of the two cones would be also the same as the radius from the sphere. So what this really means is that we could find the volume of one of these cones and simply add another volume of a second cone to determine the volume of a sphere. But this isn't necessarily the most efficient way. If we analyze the relationship between the radius of the cones and the height of the sphere, we'll see that 2 radii is equal to 1 height of the cone and 1 height of the sphere. So rather than calling the height of the cone h, we could essentially replace h with r plus r, or 2 times r. Following mathematical convention, we'll bring the coefficient of 2 to the front of the term. And simplifying r squared times r, we get r cubed. Simplifying further, we'll notice that we have two fractions, 2/3 pi r cubed plus another 2/3 pi r cubed. So let's write this a little differently to make it look a little easier to work with. While we can likely see that 2/3 plus 2/3 is 4/3, let's put them together to make this a little more obvious. Since we have a common denominator of 3, we could put our 2 plus 2 in the same numerator over one denominator of 3 to get 4/3 pi r cubed, which can also be written as 4 pi r cubed over 3.
So back to what we have just seen from that video. The formula for the volume of a sphere, as we just saw as he kind of went through all of that process, the formula for the volume of a sphere was 4/3 pi r cubed. Sorry, I'm trying to get my pen to turn on. Volume was 4/3 pi r cubed. Now, oftentimes, as we saw in the last lesson, we also have to be able to look at a hemisphere. And a hemisphere, remember, is just half of a sphere. So if I wanted you to write a formula for the volume of a hemisphere, I could take my formula for the volume of a sphere, 4/3 pi r cubed, and I could take half of that. So in other words, multiply by 1/2. Well, mathematically, if I multiply 4/3 by 1/2, I'm going to end up with 4/6 pi r cubed. And then if I reduce my fraction 4/6, I will end up with the formula of 2/3 pi r cubed for the volume of a hemisphere. Okay, so now that we've got a couple of formulas, let's look at a few application problems. We'll start with a very basic. If a sphere has a diameter of 10 inches, what is the volume of the sphere? What is the surface area of the sphere? And what is the volume of the hemisphere? Okay, keep in mind if the diameter is 10 inches, then we know that the radius will be half of that, or 5 inches. For the volume of the sphere, our formula is 4/3 pi r cubed. We'll plug in that radius of 5, and then we can do some simplifying. Now, 5 cubed is 125, so we've got 4 times, let's do 4/3, times pi times 125. 4 times 125 is 500 pi divided by 3. And since 500 cannot be divided by 3 evenly, I could either leave it like this. Remember that the units for volume are going to be cubic units. So we're going to say inches cubed. And the reason that those are going to be cubic inches is because in the formula, we are actually cubing the radius. So we're cubing that unit. Now, if you don't like the answer written with the pi, we can put this in the calculator. 500 pi divided by 3 gives us approximately 523.6 inches cubed. So that was the volume of the sphere as a whole. The surface area of the sphere, remember that surface area formula is 4 pi r squared. We're still using that same radius of 5. 5 squared is 25, and 25 times 4 is 100. So the surface area of the sphere is going to be 100 pi inches squared. And again, watch your units. With surface area, we are only squaring the radius. That's why we are only squaring the units. If you prefer having this in decimal form, 100 pi is the same as 314.16 inches squared. And then our final example was finding the volume of the hemisphere. Now, you could actually do this two ways. Some people might prefer to go back up to the volume of the whole sphere. So the volume of the sphere itself was 500 pi divided by 3. And since we're dealing with a hemisphere, we're going to take half of that, multiply by 1/2, and then we can do some simplifying. 500 pi over 6. Now, 506, we can reduce that. If we divide both of those by 2, we'll get 250 pi over 3. Since 250 divided by 3 doesn't go evenly, I would leave it like this. My units for volume are inches cubed again. So that was option 1. The other option would just be to apply the formula that we learned. Up here, we discovered that the formula for the volume of a hemisphere was going to be 2/3 pi r cubed. So the radius is, again, 5. When I multiply 2 times 5 cubed, remember that 5 cubed is 125. 2 times 125 is 250 pi over 3. And once again, inches cubed. So it depends on if you've already found the volume of the whole sphere. You could start with that and take half of it, or you could apply our formula that we had learned. Okay, a second application would be if a sphere has a surface area of 250 centimeters, and you may or may not notice that the squared got cut off. But if a sphere has a surface area of 250 centimeters squared, what is the volume of the sphere? Well, let's start with what we know. The surface area formula is pi r squared, 4 pi r squared, excuse me. We know the surface area is 250, so if we plug that in, this should allow us to solve for the radius. Again, we're going to have to start by dividing by 4 pi. And remember what we've talked about before, when you do 250 divided by 4 pi in your calculator, make sure that you put that 4 pi, that denominator, in parentheses. So when I do 250 divided by parentheses 4 pi, I'm going to get about 19.89. The 4 pi will divide to become 1, leaving us with r squared. Then we'll have to take the square root of both sides. Now, without rounding it, so leaving the answer in your calculator, I'm now going to take the square root of that answer, and I'm going to get a radius of about 4.46. And again, you do want to try to take the square root without rounding. Once we've gotten this radius, now we can kind of go on with this. So now that we know the radius, we can come over and find the volume. Volume is 4/3 pi r cubed, and now we have a radius to plug in, 4.46 cubed. Now again, if you already have this value in your calculator, rather than rounding it, I'm going to take that value and immediately raise it to the 3rd power. Then I'm going to multiply that answer by pi. So I can do times pi. And then I'm going to take that answer and multiply by the fraction 4/3. And we get about 371.69. This is volume, so this is going to be back to our centimeters cubed for our final answer. Now again, one thing to keep in mind, try to do as much of this problem without rounding so that the only time you actually round is at your very last step. I would highly recommend that you pause at this point and take a minute to go through these steps on your calculator. See if you get this exact answer without rounding anything until that last step. Once you've had a chance to try that problem, and hopefully you pause the video to do that, let's look at one more quick application. A spherical scoop of ice cream has been placed on top of a cone as shown. If the ice cream melts completely, will it overflow the cone? So ultimately what we're trying to figure out is, if this ball of ice cream were to completely melt, and when it melts, we're going to assume that it's going to fall down inside this cone here. Will it fill up this cone? And will some of it go on outside of it? Okay, so what we really need to do is compare the volumes here. First thing we need to figure out is what is the volume of the sphere, and then we're going to have to figure out what is the volume of the cone, and we're going to have to compare these to see which one is larger. So using some of our formulas, the volume of the sphere is 4/3 pi r cubed. The radius of our sphere is right here. It's that 3 inches. So if we plug that in, 4/3 times pi times 3 cubed. 3 cubed is the same as 27. I like to simplify, so I know that 3 goes into 27 9 times. And then I can multiply 4 times 9 to get 36 pi for the volume of my sphere. Now you can leave it in this form, or you can get the decimal. 36 pi is approximately 113.1. Okay, in terms of the volume of the cone, remember that volume of the cone, we do area of the base times the height, and we divide by 3. Since it's a cone, the base is in the shape of a circle, so that will be pi r squared times the height divided by 3. Now if we go back to our diagram, the radius of our cone is this 2 inches, so we'll plug that in here for the radius. The height of our cone is 4 inches, so we'll come back and plug that in for the height. So we've got pi times 2 squared times 4 divided by 3. 2 squared is 4. 4 times 4 is 16. So now I've got 16 pi divided by 3. Now right here, some of you could probably compare these right away and be able to tell that 36 pi is much larger than 16/3 pi. If you are not able to compare that right away, convert this into a decimal. So 16 pi, then divide by 3, and we're going to get about 16.76. So as we can see, the volume of the sphere or the ice cream is much larger than the volume of the cone itself, and therefore the question, will it overflow the cone? Of course the answer is yes, it will, since there's much more ice